this a bit. Okay, thank you very much. Today I gotta talk about something that is not related to my work, so that's more fun. It's NLP projects that I set up myself, and it's about like machine, like understanding how we speak and try to mimic how the style that somebody speak. So yeah, let's dive into it. I would briefly introduce myself, although I was introduced briefly. I'm a data scientist at Hotel Beds, and I'm also a co-organizer of AI Club for Gender Minority, trying to help people who are identified gender minority to get into the industry and learn and not be scared. Also, I'm a member of Python Sprint. Yesterday we have a lovely sprint to be contributing to DayUtil. I think it's amazing, and I thank very much for the sprint to bring me into this open source world. I think everybody needs to try it out and give yourself a chance. So why I do this project? I think mostly I was inspired by there was a news about somebody write a fan fiction of Harry Potter using AI, and the result is hilarious. It's very funny because you can see even the title already sounds very funny, like a pile of ash. Is that title? Is it about the ash? Yeah. So I was investigating in it to see can I do the same thing with deep learning? Because at that time I was very interested in deep learning and want to use neural network to do something cool. So luckily today I have the chance to show my my result to you. So I'm glad. This is a side project. It's fun. So my approach is very naive and very similar. I just want a very simple neural network that I can play around with. It's not going to be take me weeks to train. It's going to be I just want to understand how it works and maybe hopefully get some decent result. So it's very simple. It's only 4 layers. It's only 4 layers. It's, I don't know. Can I call it this like a deep learning? Maybe it's shallow learning, but it used some very core elements of deep learning in NLP task. For example, there will be word embeddings involved. There will be RSTM, which is a recurrent neural network that will be involved as well. I will explain a little bit more later. But we also need an input layer and output layer, right? So input layer, we have to encode our paragraph or sentence because basically machine is, if you dive deep down, machine is just like 0 and 1, so everything is numerical. So I'm trying to encode it by feeding it with everything in it. We call that a corpus. So feed it in and try to label each word as a number. So that's the encoding. But after that, I have to make it like a vector. So I do a one-hot encoding of it. For example, if there is a word that is labeled 22, so when I put it as a vector, everything will be 0 except the position 22. It will be 1. So that's one-hot encoding. You can use that to do something with it, but that's not the best way because as you can imagine, a corpus could have lots of words, and the vectors will be very big, and the matrix at the end will be very sparse. So that's not ideal. And also, it is kind of take care of each word independently. It doesn't have the magic that the word embeddings could do. It's like the logic within the words is lost. So I will also explain that when we talk about word embeddings. Also, yeah, we have to store our the mapping of our encoding because at the end we want to generate a paragraph. So we want to see if we predict a number at the end, like what does it represent? Which word is it? So we need to store that mapping as a dictionary. So yeah. So we have that magic, word embeddings, RSTM, and at the end we have the output. The output is actually, I'm not predicting just one single word. I'm trying to predict, because everything is a vector. So at the end, I would try to predict a vector as a result. So I use a softmax layer for that because it would give me a distribution of as a vector. So with this distribution, I can actually use a way to do, sample a word out of it. So why do I do it? Because when we write something, we have the creativity, so it won't be the same every time. Even though like a word that is unlikely to come after a sentence, it will still have a chance to appear like it's just a smaller chance. So I would rather have a distribution of probability to draw this word, but not hardly just predict a word. So that's the setup. So what's word embeddings? As I said, it's like a magic. For example, you can see from the graph, we have like different words is in a vector space, right? It's it's very sci-fi. It's like a vector space. But what's interesting about this space is that we can actually do calculation with words. For example, a very typical one is king. You have the vector, and then if you do the vector, some mathematics with vectors, you can have like king minus man plus women equals to queen. And actually, that's the vector space. And if we put it, this is a demonstration, so it's 2D. It's like very easy to see, like, oh, actually that's the logic. And also not just this one may be in the same space. We can also have Paris minus France plus Germany equals to Berlin. So and it's high dimensional. So you can see all the logics is we try to preserve all the word logics inside this space. But how can we gonna achieve that? This is blown my mind. How can we gonna achieve this mapping from just like 0 and 1, just like hardcore one hot encoding into this embedding space? We have we have two popular approaches. We also have more, but I will focus on two today. One is GloVac. The other one is work2vec. I will have a slide for that. So yeah, let's see what it is. The GloVac is a global vector for word representation. I have to look it up for the name. It's like I just think that GloVac is a very beautiful abbreviation, and I just remember that. So it is a count-based model. What does it mean? It's like when we train it, when we try to find this mapping, we have lots of words. For example, we scrape corpus from Wikipedia. That's what I'm using today is a corpus from Wikipedia that you can see from the paragraph, you can see the relations of the word by their coexistence. For example, in a sentence that, the teddy always come with bear. So it's like teddy bear, you can see like, oh, they are related. They are talking about the toy. And so that's by the relations from a paragraph, we can kind of build this space because we see their occurrence, like how often the two words come together. So it's a count-based model. So and then from that, we can create a matrix of that counting occurrence, so we can map it from our original space into this new word embedding space. For work2vec, I don't know, like, is it words to vector? I don't really like scratching my head. I was like, I think so. Yeah, very obvious. And it's a predictive model. So it's basically the logic of doing it is rather than just counting the co-occurrence, it's more like we train this weight by a neural network. So it's like a a neural network predictive approach. So that's why it's called a predictive model. It's just a contrast with the GloVac. And so we use a neural network to achieve that. So the first example today I'll show is like we use a work2vec, which we train it together with our model. But the second one, I will show that what if we feed a pre-trained GloVac word embeddings, and how does it compare to when we train together with the model. So I'll show you later. The second, remember we have like two magic layers. The second magic layer is called LSTM, which is long short-term memory. So the idea is that we have short-term memories. We tend to choose, we know what we remember and what we forget. For example, like you remember the happy things in your childhood, but maybe you forget all the things that you learn in schools. So that's how our memory works. And because with this neural network, it's supposed to be long, so it's called a long short-term memory. And yeah, it's a recurrent neural network. What does it mean is that for a normal neural network, all the vectors is coming in like without relation with the previous data that you fit in. But for a recurrent neural network, when you train when you train these set data, the previous data that you fit in actually affect or will train together, so it will have some relations with the previous data. So that's why it's called recurrent neural network. I will skip some of the details here because it's hard to talk about all this math here. So I'll just skip it. And also the general idea is like for long short-term memory, we have some gate. So it's control what to remember, what to not. So that's why it's very powerful because sometimes you have lots of data. You can't store everything. So this is very good. Okay, let's see if we have time for some demo. I hope we still have. No internet connection, why is it the case? Could somebody help? Yeah. 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 Well, okay, how much time do I have?
You have like 10 more minutes. The talk ends at 45.
Okay, it's fine. It's fine. I have time to log back in again. It's always happen. Don't worry. Yeah. Does it work now? Let me try again. Let me try it again. Sorry, do you have any questions? Maybe I can take some questions while I try to log back in. Yeah, I think I'm logged in. Sorry. Questions? Yeah, yeah.
Don't be shy.
I need some help to go back to the internet. Yeah.
No, but it's... Sorry. But we need to record the question, otherwise people don't hear.
So glove and word2vec seemed similar, but obviously calculated in different ways. When do you use one or the other? Is there any kind of wisdom on that?
Yeah, obviously for GloVac, you have to be careful what you fit in because, for example, in my case, what I'm meant to show you is that I have a pre-trained GloVac, which is pre-trained from Wikipedia. So I have actually two demo tasks. One is Shakespeare, one is Trump. So for the Wikipedia, it's written in modern English, right? So you can't really use it to do the Shakespeare one because it won't be as good because it's it's modern English. It's not exactly like what Trump will speak in Wikipedia, but it will be better, like if you do something in English. So it really depends on your task and the GloVac model that you fit it in, the state mesh. Like sometimes if we can't find the pre-trained model online, we have to build it ourselves as well. GloVac, you can also train it yourself, but I think it's easier if you can download it. And the Stanford, they have a very good library that you can download. That's where I got my thing. Yeah. So yeah, we can check it out now. Yeah. So this is the Shakespeare one. Let me see if I can run all of them. Yeah. It should be fast. I hope so. But yeah, let's look at the other one. Okay, it's running, which is good. Okay, yeah, it's training here. So yeah, what it does, I walk a little bit through it. Is it too small? Let me make it bigger. Oh, it's too big. This is not my computer, by the way. So yeah. Okay, is it okay? Yeah. Okay. So do here is like I have two helper functions. One is for Trump, one is for Shakespeare. So I'll only use one of those here. It's bad coding habit, but just bear with me. So here we load in the play for the Shakespeare. So if I scroll it a little bit more so you can see, yeah, it's spoken in some English that is very Shakespeare. I don't know what else to say. Yeah, very elegant and things like that. And yeah, so I fit in 5 plays, I think. So it's got to be with comedy and tragedy. I want to balance it out. I don't want it to be always sad. So I put some of them, not every single word by Shakespeare in. And so this is you have to also set the maximum number of words because you ain't gonna capture everything if it's a big corpus. So you have to set the limit. So for words that's not within it's not frequency enough to be represented, it would be just as like unknown or something like that. Yeah. So yeah, let's fast forward. The model is yeah, this is the model that as what I showed you before. There's a lot of parameters, and we have trained it. We just trained it for one corpus because this recurrent neural network is a small neural network, and I've tried with two epochs. Yeah, I just trained with one epoch here, and it's actually trained it for one more epoch doesn't really improve the result. So that's why I stop it there. And also, when I generate a paragraph, as I said, so it's got to have a sampling function that is going to sample the probability from the prediction of the softmax output, the prediction of the what's the probability of the next word. I will sample it from there. So also you can tune you can give it some more noise, so it has higher chance to pick something that is less likely to be the next word. Yeah. So I think this is the most interesting part, the result. Let's see how it goes. To anybody who is like a Shakespeare expert, no. So do you think this is a good paragraph? Because English is not my first language, and I didn't study Shakespeare when I was in school, so looks all right to me. Let's see Trump, it's easier to understand. So basically, everything will be the same here. I think I won't show it again because it's got to be the same thing, but I'll show you the result here. So yeah, this is what I fit in. This is all scraped from all the Trump's speeches. So somebody record it and write it down, because when you are president, you give a speech. Somebody will, have the transcription, so they can, the people who doesn't, they can have access to it. And so same thing. We have build a network that, as what I told you in the slides, it's got to be the same thing. There's a minor difference with the previous one, because I've changed this embedding space to be 200 because the GloVac, the embedding space is also 200. So I want to mesh both of them. So as a comparison, so that's why I changed it. It doesn't affect it that much actually, but we'll see. So this is by the work-to-vec approach. This is what is generated by work-to-vec. And so you can see that it's still a bit nonsense, but you can see there's some logic inside. Let me see if I can find one. Yeah, for example, this set once, believer, something. It's it follows certain logic in words. Like for example, following a noun, it would be a verb, and all these. But it's still like crazy man speech. Not as, I mean, who is crazier? I can't tell you. So compared to GloVac, one thing I want to point out is that actually it's faster to train with the pre-trained GloVac, which is as expected because the word embedding layers, we don't have to train it. So there's less parameter to train. But the losses is actually quite high. That's what I'm trying to say, is because it's not as good as I have a GloVac that is trained from my corpus, so it's only from Wikipedia. It's not it's not exactly what I used to train the model. But you can also it sounds bad, but it could have its advantage, because what if your, for example, Trump only give 1 or 2 speeches that I can, get the transcript. So I don't have a lot of words to train my own, representation. Then maybe downloading like a pre-trained model, like pre-trained word embeddings from Wikipedia, like from Stanford that use Wikipedia, which have like loads of words. Maybe that could be better than training my own, because I don't have a lot of data to train it. So yeah, so this is Glovac. I try to fix the seed, so it's kind of giving me the same generating sentence. So it starts with the same point, and to see the two, so it's giving the same starting point. It's like to compare the two models. Are they like giving the result? Which one is better? Which one I like more? So this one is different. I would say I like the Work2Vec one more. This one is also you see like demonstration fans like Brooke and those. Yeah, it's also similarly have like some logic, word logic in it, but it's still a bit crazy. So yeah, this is my side project, and this is the fun that I had, and this is the result. And I think yeah, I would just like let you ask question and have lunch.
That was really interesting. Thank you very much. I wondered, looking at all of the examples, one of the things that they kind of miss is the end of a sentence. I guess it's very easy to have a model that takes one word and then finds another word after it that makes sense. It's harder to have a higher level view where you're like the end of a sentence. It's one of the very distinct things about Shakespeare is that he has like iambic pentameter. He has like a line and then a new line, and that's like. But with you, I guess it's quite hard to find the point where you end a sentence.
That's a good thinking. Actually, you can include, as I said before, if you can't find that word in the model, you can have something that is unknown, that is like encoded in maybe one of your word is actually unknown, representing all the unknown word. But you can also have end of line there, so you can train your model to know when to stop the line. I didn't do it here, but it's doable. So that's one way to improve this project.
So it's still micro. It's not like high-level view of this is a sentence. It's just like after this word comes end of sentence. Basically, full stop is another.
Yeah, that would
variable.
be, because end of sentence is treated as one of the words. So it will, I will predict, for example, every time I say thank you, that would be end of line. So it will actually train the model to see, when it says thank you, so the very high chances that will be an end of line following. So you can actually stop the sentence there. So it's possible.
Hi, thanks very much for the talk. Just following on from the last question, you mentioned iambic pentameter. So this is one of the things that we can spot Shakespeare by the number of syllables in a line. Have you used integrated neural networks to look at syllable recognition as part of this?
For this project, no. It's a very, as I said, very naive, simple, fun model. But that's a very good inspiration. I think, yeah, it's something that interests a lot of researchers, and I think it's a good point that you pointed out. Yeah.
Oh, do you want to do a follow-up? Oh, okay, sorry.
Do you have the code for this up somewhere?
Yes, it's on my GitHub. I think I would try to see if I can, if you go to my, let's see, I can, no, sorry. Yeah, if you go to follow me on, I'm selling myself now, as promoting myself. See if I can go back. Yeah, if you add me on Twitter, once I finalize the slides, I'll upload it, and there's the link. The demo. There's like a HTML like thing that there is like you can go to my GitHub, and then you will find the codes there.
Yeah. Have you played around with different ways of generating text? Have you compared the output, something like the Markov chain models to generate text, and kind of compared like which one makes more sense when you get the output?
Yeah, okay, I'll advertise myself even more because I have another one on GitHub that is using n-gram and Markov chain to do a predictive word model. Actually, by the way, the Harry Potter thing that actually I found the source where they use is actually they have similar thing. It's like they have the predictive text. It's similar to what I did, but I didn't do Harry Potter. So when you click actually, if you have my slides later, and then you at the end there's like a reference. Actually, I can show you now. So they have predictive text. So I'm not so sure which model they are using, but for the thing that I did on my GitHub is actually that predictive thing. But I think it's very interesting. Let me show you this. It reminds me. And where's Harry Potter? He's here. I found it yesterday. Yeah. So, but this is different from my approach because my approach is purely done by the AI and machine. Maybe the internet is broken again. Whatever, you can go to the link yourself and play around with it. This one, you click on one word and it will give you the next word. So you can write your Harry Potter fiction by clicking it. There's some human influence in that one because when you click on the next one, you actually choose the next word. But for me, my model is just drawing from that distribution, so there's no human picking of it. Yeah.
So sadly, we are out of time.
Oh, sorry.
Thank you very. No. It was amazing. Thank you very much. Please give it up for her.
Thanks.